So in these last 2 weeks that we have been talking about sampling distribution, we have learned about chi-square distribution, t distribution, f distribution, and the binomial distribution. How is it related to your normal distribution? So all these we have looked at. So now it is also important to see how you can visualize these distributions in Python. So let us begin that, and for this we will first of all start with the visualization of chi-square distribution, which we have seen plays a very important role when we are talking about your sample variance, and because of its close relation with the standard normal distribution as well. Also it is related to the F distribution, as we have seen in the last class also. So let us start with that. So for this, as we know, first of all we need to import certain libraries. So import numpy as np. Okay, so for numerical operations we will have this, and import matplotlib.pyplot as plt. Okay, so this will be used for creating the plots, and from scipy stats module we are going to import chi-square. So basically chi2. So this is basically a function which is used for working with your chi-square distribution. Next, we would define a range for x values. So let me just write x is equal to np.linspace, because it's a function in numpy library, and basically it is used to specify the range of values that this x array would contain. So here it would start from 0 to 20 suppose, and you need 1000 equidistant points between these two. Okay, so this would basically create an array x. Now you can define the degrees of freedom also, because in chi-square we want to show the chi-square distribution for different degrees of freedom. So let us specify what degrees of freedom do we want. Suppose you want to see for the first 6 ones. Now you can plot this figure, plt.figure. We can specify the fig size as suppose 12 by 8. Now we will initiate a for loop that will iterate over these degrees of freedom, and for each degree of freedom it would calculate the PDF values, and then it will plot that figure. So likewise it will keep on going for these 6 degrees of freedom. So to initiate that for loop we would write for dof in this that we have over here values, so that to differentiate it with this variable. So dof in these values we would find PDF, which is chi2 dot PDF, where x is the input that we have obtained from here, and your other one would be the corresponding degrees of freedom. Okay, so for each degree of freedom in this list that we have created, it would calculate the PDF values for the chi-square distribution. Here chi2.pdf is basically a function from your scipy library, which is used to display the chi-square distribution values. Fine. So after this we can write plt.plot. X would be there, that is x-axis. PDF would be the density that we have, and we want to label f degrees of freedom is equal to dof, because first it will evaluate this string and then we will solve it further. plt.plot x PDF, label is this. Fine. Now you want to set the limit of y-axis to start from 0 to and end at 0.5. So let me just write it 0 to 0.5. Okay, if you do not want that, you can change this right? You can make it up to 0 to 1, because sometimes when you take it in a wider range, then the other graphs become very cluttered around each other and it does not give a good visualization. So for that, it is better to specify it. Then obviously we can write x label. So let us label the x-axis as simply your x. Sorry, it should be a curly bracket over here. Then what will be your y label? Y label, we can just simply say the PDF. We want this to appear. And the title would be chi-square distribution. Chi-square distribution for different degrees of freedom. So we can just mention this much. We want the legend to appear. Plot.legend. And then if you want the grids, then you can mention this as true. And finally, we would display the plot that you have generated so far. Yes, so this is what you have made over here. You can see that x-axis over here, we have displayed the x label as x. On the y-axis, you are displaying PDF, and the overall title of this plot is chi-square distribution. And in this legend, you can see that it is displaying which color represents which degrees of freedom. Okay, degrees of freedom is equal to 1, because this is what we have written over here, right? Suppose let me just write DOF. If you just want the degrees of freedom, it would give you like this. Okay, and it is displaying, so you can see that for 1 and 2 it is in this shape, right? Blue one, and this one is orange. And when you are increasing the number of degrees of freedom, the shape is now changing and it is becoming right skewed. It is becoming less right skewed, and moreover it is start going, if you take for larger degrees of freedom, it might even be becoming normal. So maybe we can make here, suppose 6 instead of 6. Let me see for 10 what happens. You see, for 10 degrees of freedom, you see that it has become more and more symmetric. We can further increase it to see the pattern. Suppose for 15 degrees of freedom, it is going like this, right? Because here we have restricted it to 0 to 20 only. In this case, suppose you take it to 0 to 40 and then run this, so you can see. So depending upon the degrees of freedom, the shape of the chi-square distribution changes, because that is the only parameter in your chi-square distribution. And if you increase the degrees of freedom, as you move ahead, this shape will become more and more symmetric. At some point it will become nearly symmetric, that is your normal distribution, and so on. Now another important distribution that arises from your chi-square and the standard normal distribution is your t-distribution. So basically in this one, we have plotted in the same plot, we have displayed multiple chi-square distribution curves, and each with its unique degrees of freedom. Okay, so you can compare these plots with respect to the degrees of freedom, and you can see that how the degrees of freedom basically affect the distribution shape. Okay, so in this one also, let us do for the t distribution. So we need certain libraries. So NumPy we already have, matplotlib I think we also have that. Let me just check it. Yes, from scipy.stats we have imported chi2. Now in this case we need some other library, because we would be working with t distribution, so we need t function over here. Okay, now we would define a range of x values for this plot. So let me just write it. So x would be n from NumPy library. Again in the same way we would define it. X np linspace, and it will go, suppose from -5 to 5, and we need 1000 points in between. So basically it is creating an array x containing 1000 evenly spaced values ranging from -5 to 5. We are giving this range because for t distribution it is similar to your normal distribution and its range is from -infinity to infinity, unlike your chi-square and f distribution where you can see that it starts from 0 to infinity. Okay. Now again we would define the degrees of freedom. So DOF values for the same degrees of freedom we will see, or you can change it also. Suppose this is 1, 2 and 5, 10, suppose 20 you are taking. So you have created a list of these degrees of freedom. Okay, and we are going to first of all mention the size of this plot, and then plot dot figure fig size is equal to 12 by 8. So now you would initiate a for loop, and for each degree of freedom it will choose from here, it will plot the t distribution and then it will keep on moving like this. So let me just write for DOF in DOF underscore values. So you can see that it looks similar to your earlier one. PDF is equal to t dot PDF. So here we are using this function from your SciPy library. So here it would be x comma PDF, sorry DOF, because the degree of freedom we have to specify, and then we will plot it plt dot plot. X would be there and then the PDF, that is the value that you have calculated, and we can label it and we can use this f string over here, degrees of freedom. So maybe just I can write DF is equal to, here we would write DOF and after this. Okay, so first this DOF will be evaluated from this loop and then it would print it. And here we can simply print your X label, Y and all other things. So we can write plt.x label. Again we can use, suppose X values are there. Then for Y label we can have the density, suppose, and the plot title would be, because this is t distribution, so let us just write its full name, students t distribution for various degrees of freedom. And your next one, suppose you want the legend, so it would come this way. Then grid can also be added. If you do not want, we can leave that. Then we can show this plot, so you can see how it looks like, right? Or if you want to add this grid, sometimes it makes more sense to add these grids because it is easy to interpret in that way. You can see the corresponding values on the X and Y axis. So here basically you have generated these t distribution for varying degrees of freedom. Okay, one is this one, you can see blue, and as you can see here it is varying from, suppose, somewhere -5 to 5, right? Because that is what we wanted. We wanted from -5 to 5, we wanted 1000 equidistant values, and these are the corresponding Y axis. Okay, so it first chooses 1 degree of freedom from this, finds the PDF, that is this one, Y axis, and then it plots that and it displays DF is equal to the degree of freedom, that is 1. Again this it will go and it will pick another degree of freedom, and this loop will continue till all these figures are made, and then you can finally label your X and this. So you can note that here this, when by writing this, so indentation over here is important, because if you write leftmost corner, if you shift this plot to anywhere else, then it basically means that it is not considered in this loop, so it will not draw this plot. Okay, and if you, since you want it to be created for each degree of freedom. So you need to keep it in a way such that it is read in that for loop itself. Okay. So you can see that the t distributions becomes more similar to your standard normal distribution as the degrees of freedom increase. Next distribution from this chi and t, and then I can probably add these comments over here. So this is basically visualization of chi-square distribution. Okay, and this one is your visualization of t distribution. Now here we can go for your f distribution. F, if you remember, it is the ratio of your two chi-square distributions divided by their respective degrees of freedom. Okay, so it also has a similar shape as you have for the chi-square. It varies from 0 to infinity. So for this also, already we have numpy and matplotlib, so we will import from scipy.stats, we will import your f function. So from scipy.stats import f. Okay, so again we can define this array over here. So let us see what is the range for x values, line space. So we can take from 0 to 5 and we can keep 1000 data points in between. Next, in f distribution you have two degrees of freedom, m and n. So we need to define those m values and n values. So suppose you need to see for m values, let us say these are the 1, 2, 5, 10 and 50, and we have this your n values basically as 1, 3, 5, 10, 50 for the same basically. So here we have just changed one, otherwise if you see for the same degrees of freedom in the numerator and the denominator, m values and n values have been provided over here. So these are the list that contains these degrees of freedom. Now we want to create the plot and we will specify the figure size. Sorry, plot.figure fig size is equal to fig size is 12 by 8. Okay, so it will create a figure, and again we have to initiate a for loop, right, so that it iterates over each of these pairs of m and n values and draws your f distribution plot. So for this we need both m and n values. Okay, for mn in zip, so here you have m values and n values. Okay, so basically this we are using over here zip function. Basically it is used to pair corresponding elements from m values and n values, this list that we have. Okay, and in each iteration these m and n would be set to the current pair of values that has been selected. Okay, so for m and n we will calculate the PDF, which is f.pdf. we are using this function over here, PDF. X would be there, m would be there, n would be there, because here we are saying that for m, so m corresponds to m values, n values, and n corresponds to n values. So that is why we are using the same thing over here. If you can see from here also, we have written the DOF values for DOF and DOF values. So that same variable that we have defined here, that comes over this line. Now we write this plt.plot. X would be there, as you know, PDF would be there, X and Y axis we have defined. Label, suppose you want f So you want m values also, so it can be given as m, and for n it would be evaluated and then substituted over here. Okay, so this would create the plots, and you can now mention the labels also. All right, we can just use the same things and we can edit it. So x, this is fine, so we can write here f distribution. Okay, so let us see how it is displaying. Okay, so for different values of m and n, you have obtained these plots. So if you want, suppose here these are not clearly visible, so maybe we could limit this y-axis. So for that we can add one more line over here, plt dot y limit. Let us keep the top as 2 and bottom as 0, so it will go from 0 to 2 only. So if you run this, so now you can see that in the y-axis you have only marked till 2. Okay, and these plots are clearly visible in this case. So we see that we can compare these distributions for different values of m and n, and it can be seen that it has a similar way as we have done for the chi-square also. Initially it is right skewed, but then as the degrees of freedom increases, it becomes more and more symmetric. Okay, it approaches your normal distribution. That is why your normal distribution has so much significance, not only in statistics but in all the disciplines across engineering disciplines and sciences, because of the central limit theorem also. And if any distribution that you use, you can justify it that obviously it was going to end up in a normal distribution, most of them. So these are the ones for mean and variance. We have come across these things. When we are dealing with mean, we have this t distribution. When we have chi-square and f are used for sample variances, or you have ratio of sample variances. And for the proportion, we use your binomial distribution. Okay, so now we are going to plot the binomial distribution with different n and p. So here, so we have numpy and matplotlib. So from scipy dot stats, we are going to import binom function over here. Okay, we are going to define a range of x values. So x and p from numpy, we will use a range from 0 to 21. Okay, so it will create an array. It will contain the values from 0 to 20. As we know that it will not include the end one, it subtracts 1 from that, so it will go from 0 to 20. So these basically, x represents the possible number of success in the binomial distribution, and that will be used in the x-axis. See, in binomial we have two parameters, n and p, right? And binomial basically says that number of success in an independent Bernoulli trials. So you need the number of trials that have to be fixed. You have to fix the probability of success, and you need those x, right? How many success are there? So number of success we are taking as this. Now we need also to define your n values. So let us say that it is 10, 20. Okay, so these are the number of trials, and the corresponding p values let us take as, suppose p, let it be 0.5. Okay, so this will create two lists over here, n values for n and p values. Now since there would be, this is a discrete case, so in this one we cannot just connect these points as we have over here, these plots, right? So for that, let us first define certain colors and see that how it would help us in finally visualizing the binomial distribution. Okay, so let us define the list of colors. So let the colors be be blue, green or red. Okay, now we can specify the figure size, figure, and fig size would be 12 by 8. Okay, so it will create this matplotlib figure. Size, width will be 12 and height would be 8 units. Now we will just take this also, color.idx, so it would basically be indexed for cycling through these different colors. Okay, so color._index, we are specifying it as 0 as of now. Now we want to create a loop that would iterate through different values of n and p. So for that, for n in n values, okay, and for p in p values, we calculate the PMF. So here we have the PMF, so we will use this binom function over here, binom dot PMF. So x would be there, n and p would be there, right? And it's a discrete case. So suppose you want vertical lines starting from x axis to those data points. You do not want these curves. So for that, instead of using pplot, so we will here use vlines, plt.vlines. Okay, so vlines x, we would specify x, that is already here, and we want it to the lines to start at x-axis. That means y would be 0, so this 0 is coming. PMF would be there, and then label would be there, that how many fn is equal to n, so this would be evaluated, and for p also it would be evaluated. Okay, and you can specify the colors also. So colors, it should keep on updating. So colors, we can write color idx. Okay, so basically we are specifying the colors of the vertical lines, right? So suppose we want blue color for a separate binomial case when you have n as 10 and p is 0.5. The next could be green color will be used for 20 n and 0.5 p. Okay, so here we have defined and we have written it in this order, so it will move on. Okay, so it uses this color idx, this variable, to select a color from this colors list. Okay, now we also want this color index to move, so idx is equal to, so in bracket we would write color underscore idx plus 1, then we will use the mod of this modulus function, length of the colors. So basically what we are doing over here is that we are cycling through these colors in the colors list. Okay, in the list that we have defined over here, it increments the color index variable by 1 and then takes the modulus of it with the length of the colors list. Okay, this ensures that when you are using this color index, when it reaches the end of your list, it will wrap around to the beginning and you will be allowed to use a different color for each different n and p. Okay, so in this way it would keep on moving. Now once you have defined these, you can simply have your x label, y label and the title. So we can use it. So x label we can have as the number of success, because in your binomial, number of success is your random variable in which you are interested. Here we will have your PMF, we can write corresponding probabilities, and this is basically your binomial distribution. Okay, plot legend This is a discrete case, so maybe we can skip this grid because there will be vertical lines also, it might create confusion, and this is also not needed in this case. So this is how it looks, right? Or if you can make this, let us see the difference. Yeah, this is also looking better. So you see that these are the blue, so here it is overlapping with this green, so you do not see it clearly. But for N and P, it is in this way, right? It is, you can see that is more and less like a normal distribution. So N is 10, so the blue one corresponds to N is 10 and P is 0.5, and whereas for 20 and 0.5 it is this. So if you change this, suppose 10 and 30 we take, the sample size is 30, then you can see that it separately plots these two because there will be some distance in these values. So by just looking at these two, you can see that how these distributions basically look like your normal binomial case, right? Since NP we have taken till 21, so if you want more than 3, suppose 10, 30, maybe I can take 50 and make this one as 41. So let us run this. So let us have 3 plots. Okay. So NP approximation should be satisfied. You can see that when NP, in this case NP is your 5, then also it is showing, but when it is more, right, then in this case it is becoming more and more symmetric or more and more like your normal distribution. So this basically shows how you can visualize different distributions. This is for binomial. We have seen F distribution, T and chi-square. Okay.